Welcome back to the deep dive. So I think we've all been there, right? You're trying to find that one specific image you took years ago. You can remember the feeling of the photo, what was happening, but you have no idea what the file name is. You certainly didn't tag it with the right keyword.
It's the curse of having a huge digital library. You're completely stuck with old school metadata. But the system we're looking at today, this AI image search, it flips that on its head. It finds images by understanding what's actually in them.
And that's the conceptual jump, right? This isn't just a piece of software we're talking about. It's more like a blueprint for building a search engine that doesn't need you to do the hard work.
Exactly. Our mission today is to really break down how this thing is built. We're going to look at how these specialized AI parts connect, how a vision model like LLaVA generates the descriptions, and then how an indexing tool like FAISS lets you find what you need in a split second.
So if you're a learner and you want that aha moment about how modern AI really works under the hood, outside of some giant cloud service, this is for you. This is how you build it yourself.
Right, so let's start where any user would, the experience. What does it actually feel like to use this? What makes it better than just, searching through folders?
Well, the first thing that hooks you is the automated part. The system basically assumes you hate tagging photos.
A safe assumption.
Very safe assumption. So you feed it your images. And LLaVA, this vision AI, it just goes to work. It writes a little 2 or 3 line description for every single photo. The AI is doing its own tagging.
Which is a massive time saver.
Yeah.
And it can pick up on things a human might miss, Not just man-sitting, but maybe a quiet moment of reflection during a thunderstorm.
Yeah, it gets the mood. And then the search itself,
Yeah.
it's just so smooth. It has this auto search feature, so you don't type a query, hit enter, and wait.
No search button.
No search button.
Yeah.
The results they appear as you type. It feels really fluid, like it's reading your mind.
It has to be fast for that to work, otherwise it'd just be annoying. But when you get those instant results, you need to know if they're any good. Right?
Yeah, are they actually relevant? And that's where these little confidence badges come in.
Okay, tell me about those.
They're these little color-coded tags next to each result. It's a score from 0 to 1.
Yeah.
So you can see instantly, okay, this image is a 0.98 match for what I typed, while another one might be a 0.5. It guides your eye.
So it's not just a yes or no, it's showing you a whole spectrum of relevance. It lets the system show you maybe 10 options, but it's pointing you to the top 2 or 3 that are the closest conceptual match.
That spectrum is what makes it so powerful. Now, for the interface, the sources mention you actually get a choice. There's a Streamlit app and a Gradio app.
Right. And the choice is really just about looks and feel. Streamlit gives you that, modern gradient UI, a bit more polished. Gradio is more of a simple, clean UI.
So they're just different windows looking into the same engine room.
Exactly the same. They both connect to the same SQLite database, the same FAISS vector index. The search results, the speed, the confidence scores, it's identical no matter which one you use.
And if you don't even want to search, if you just want to browse.
Then you've got the Browse All tab. It turns your messy folder of images into this smart gallery. You can sort and filter, and you see all those AI-generated descriptions right there. It really organizes your collection for you.
These features are great, but they're the surface level. To really get why this is so fast and accurate, we have to go deeper into the engine room.
Yep. Let's talk about the architecture.
I'm ready. What are the core parts that make this whole thing tick?
So the foundation is all about open source, local first tools. You need Python, of course, version 3.8 or higher. But the absolute key is having LLaVA installed and running.
LLaVA. We should probably define that because it's not just a small dependency. It's the heart of the local intelligence here.
That's a great way to put it. LLaVA is a tool that lets you download and run these huge, powerful language and vision models right on your own machine.
Stuff that used to require a massive server farm in the cloud.
Exactly. And because it's local, all your images, all the processing, it stays completely private. Nothing ever leaves your computer.
Okay, so which models does LLaVA need to be running for this system to work?
There are 2 that are mandatory. The first one is LLaVA. That's the vision model, the one that looks at the pixels and spits out the text description.
Got it. And the second?
The second is Nomic Embed text. This one's job is to take that text description and turn it into math. It generates the embeddings.
The embeddings. Let's trace that. Let's follow one image as it goes through this whole indexing process from image to vector.
Okay, it's a really clean workflow. So an image gets uploaded, immediately LLaVA is called to analyze it and write that 2 or 3 line description.
Right.
Then that text is handed off to Nomic Embed text.
And that's where it becomes a conceptual fingerprint.
Precisely, a high-dimensional vector. The sources say it's a 768-dimensional vector.
768, that sounds like a big random number, but that's the key to the nuance, isn't it?
It is. That number, that length, is what gives the system enough room to distinguish between very similar but different concepts, like a red motorcycle in a garage versus a red motorcycle speeding down a highway.
If it was only, say, 10 dimensions, it would be much clumsier conceptually.
Way clumsier. So once we have this 768-dimensional vector, this fingerprint, it gets stored in two places.
Why two?
For optimization. It's a hybrid approach. All the regular metadata file name, the description text, the vector saved as a text array, that all goes into a standard SQLite database.
Okay, that makes sense for looking things up, but that doesn't sound fast.
It isn't. For pure speed, the binary version of that vector gets pushed into something called a FAISS.
The FAISS, that's from Meta, right? Facebook AI similarity search. It's built for one job, finding similar vectors extremely fast.
Perfect analogy. SQLite is like the library catalog card. It tells you what the image is. FAISS is the specialist tool that knows where that concept lives in that high-dimensional space.
Okay, and there's a little detail here, an analyst insight, about normalization. What's that about?
Yes. So before the vector is put into the FAISS index, its length or magnitude is normalized.
Why does that matter?
Because it means when we compare two vectors, we're only measuring the angle between them, not how long they are. That angle represents the conceptual similarity. We're making sure we're comparing apples to apples.
You want to measure how close the concepts are, not how long the original description was.
You got it. So now everything's indexed. The search workflow can kick in. You type a query like, old man in a crowded cafe.
And that query text goes through the exact same embedding model.
Instantly. Your query becomes its own 768-dimensional vector. And now, that query vector is looking for its closest neighbors in the index.
This is where FAISS does its magic.
And it is magic. It performs a vector search that is just breathtakingly fast. It finds the k nearest neighbors, the k most similar image vectors to your query vector.
It's asking, of all the fingerprints I have on file, which ones are mathematically closest to the fingerprint of the query I just typed?
That's it exactly. Then the system just maps those vector results back to the records in the SQLite database to get the actual image file and description. And boom, it's on your screen, ranked by that confidence score.
That is such a tight, efficient architecture. Okay, but let's get practical. Let's say I want to do this with my 10,000 family photos. How do I even get them in there, and how long will it take?
Right, the practical side. The sources are pretty clear here. You can use the UI to upload a few images at a time.
But that's not the recommended way.
No. For a big job, you want to do bulk processing. You just copy all your images into the images folder and then run a single command from your terminal.python buildvectors.py.
And that just chews through the whole folder?
It chews through everything. It's a set it and forget it batch job. LLaVA describes everything, the embeddings are generated, and the FAISS index gets built all at once.
Let's talk about the hard numbers. Where's the bottleneck?
Well, it's not the search speed. That's a solved problem. We're talking less than 100 milliseconds for a collection of 1,000 images. It feels instant.
Okay.
The bottleneck is that initial indexing. It's the upload speed.
Which is all down to LLaVA having to actually look at and process every single image, I'm guessing?
Correct. The sources quote a speed of around 3 to 5 seconds per image. Now, you have to think about what that means. If you have 5,000 images, that's almost 7 hours of processing time.
Wow, that's a long time.
It is. But that's the trade-off. You pay that time up front for having this state-of-the-art AI analysis done completely privately on your own machine for free. You're not paying for a cloud API.
That's a really good point. You pay with time instead of money and privacy. And once that 7 hours is done, the searching is instant forever on a collection that can scale up to, what, 100,000 images or so?
Easily. SQLite can handle that no problem for a local setup.
Yeah.
But all these moving parts, the database and the separate FAISS index, they can get out of sync.
Right. How do you maintain it? What happens if I, say, manually delete an image file from the folder?
That's a perfect example. The first thing you notice is the status bar. It shows images, vectors. If those two numbers don't match, you know your index is broken.
Ah, so it tells you there's a problem.
It does. And the fix is a button in the sidebar that says, "Oh, rebuild vector index." You click that, and it tells FAISS to just throw away the old index and build a fresh new one based on whatever is currently in the SQLite database. It syncs everything back up.
That's a vital feature. Okay, but what if I want to tweak the AI? Let's say my computer's a bit older, and I trade a little accuracy for more speed.
And that's where the open source nature of this really shines. You can just pop open the code and edit the config class, holds all the main settings.
So what's a typical trade-off I could make?
The easiest one is swapping out the embedding model. The default is Nomic Embed text. But if you want more speed, you could switch to something like all minimal. It's smaller, it's faster, but your conceptual accuracy might dip a little bit. The vectors aren't quite as nuanced.
And the other way, if I have a powerful machine and I want the absolute best accuracy,
then you could swap in Mix by Embed Large. It's bigger, it's more accurate, but it will use more memory. It gives you, the learner, the power to tune that balance based on your own needs.
And you can even change what LLaVA writes, right? The actual prompt.
Absolutely. You could tell it to only focus on colors or to write a 5-sentence paragraph about the mood. You could also change the top value, which is just the number of search results you see by default.
That level of customization is amazing. We've really gone from the slick UI all the way down to the 768 dimensional vectors.
The big takeaway here is how all these specialized open source AI tools are chained together. You have LLaVA and LLaVA doing the seeing and describing. You have the embeddings turning that into math. And then you have FAISS doing the super fast lookup.
And it creates this incredibly powerful search system that just bypasses all the old problems with manual tagging. It's a perfect example of composable AI.
Yeah, and if you zoom out, the whole thing is MIT licensed. It's built with accessible tools. Streamlit, LLaVA, ACE, that makes a big statement about, data ownership and privacy.
This kind of vector search used to be something only the giant cloud companies could offer you. It meant locking you into their system, sending them your data.
So the final thought to leave you with is this. If you can combine these tools to build a system this powerful for your photos, what other kinds of knowledge could you organize this way? Think about your documents, your research notes, your company's internal data. This architectural blueprint, this shift towards adaptable local AI, is fundamentally changing how we can manage our own knowledge.